you very much for introduction. So once it was realized that gravitational waves exist and full general theory of relativity admits them, efforts started to detect them. Because they are extraordinarily weak, it took decades before instruments that were sufficiently sensitive were constructed. And as you know, which was announced last year, finally the LIGO detectors registered for the first time the gravitational wave signals, and these signals originated from a coalescence of black holes. Before I start, I will still point out to one important paper by Roger Penrose, in which he used conformal transformation to define boundary of the spacetime at infinity, and using this tool he was able to derive all basic properties of the gravitational radiation. It is this asymptotic condition, asymptotic behavior of Riemann tensor, so-called peeling-off property, also definition of the total energy. Moreover, his analysis applied not only to gravitational field, but arbitrary spin field. So next is the signal from a binary system which was detected. So here is our properties of the signals in the quadrupole approximation, the first approximation, which is enough to describe the signal up to fairly accurate, up to binary system coalesces. So both the amplitude and this time of evolution which determines the phase depends on one combination of masses called the chirp mass. So amplitude depends almost as a power of 2 of this mass. It increases with frequency, and of course it's inversely proportional to the distance. In the Fourier domain, you see that the power of the signal goes down as frequency almost square of the frequency, which means that in order to detect the signals, you need a detector that is very sensitive at low frequencies. You can also estimate from the last stable orbit of Kerr solution what's the frequency of coalescence, and this is inversely proportional to the mass. So again, if you have a detector that is sensitive at low frequencies, you can detect signals with high masses. Next is that before the gravitational wave signals were directly registered, there were indirect evidence, which the most known is that came from the timing of a binary pulsar, which is a binary system of 2 neutron stars with this characteristic time of evolution less than Hubble time. So this is the progenitor for the coalescing binaries. But there are also other systems. Paczynski points out that gravitational radiation must have played a role in the evolution of closed neutron star binaries. There is also a binary system of black holes, of supermassive black holes. So one has an accretion disk, and the smaller black hole, when passes through this disk, there are flashes. So there's an optical signal which is very strong. Optical signals from the system were observed at the end of the 19th century. And the orbital period here is quite long. It's around 13 years, but several observations were made of the system, and the orbit shrinks as it is radiating gravitational waves. The next thing is the detector. The principle of detection of gravitational waves is fairly simple. You use a laser interferometer, because when gravitational wave passes, it changes the curvature of the space-time, and this changes the travel time of the laser light. So you can measure through interference, you can measure the changes of phase. And change of phase is proportional to the amplitude of the gravitational wave. So here is some estimate of that you can measure a very small amplitude. So you measure the phase, of course, through laser light. So roughly this amplitude can be measured is length of the laser light over the length of the distance. So you see you need kilometer scale detectors in order to have sufficiently sensitive detector. Moreover, in a laser interferometer, the light bounces back and forth from the mirrors multiple times. This also increases the paths and increases the sensitivity. Moreover, you also put an additional mirror called signal recycling mirror, which effectively increases the laser power in this interferometer, which can be taught as a certain cavity. And this again increases the sensitivity. You know, this technique was invented by later on Driver. So with this interferometer, you can measure very, very small amplitudes. So of course, these detectors, in order to have to do this, to have this high sensitivity, this system has to be enclosed in vacuum in order that there's no scattering of the light. Also, there has to be a very good seismic isolation. But really, the crown jewels of the detectors are the mirrors, which are made from fused silica. Moreover, the suspensions, at least here is the LIGO design, at least the last level of suspension, the wires are also made from fused silica. This lowers the thermal noise. These mirrors are polished to an extraordinary accuracy and have extremely low sensitivity. So with this system, and moreover here there is an active seismic isolation system. So with this system you can attain a sensitivity of low frequency. And thanks to this, it was possible to detect these signals from binary black holes. So now we have a network of these interferometers. So these are two LIGO detectors, and there is a Virgo detector in Europe, and also a smaller detector in Europe called GEO. And these detectors are operating, and they were taking data, but those were, you know, the LIGO detector that made the first registration of the signal. There is also a detector interferometer under construction in Japan called Kagra, and also there are plans to build a detector in India. Okay, so here I give a more detail about the Virgo detector, which has 20 labs, 20 groups. One of the groups is a group from Poland. So Poland is one of the 6 countries contributing to this detector. This detector was originally built by Italy and France. So they provided, you know, most funding. Our group contributes to data analysis, to modeling of astrophysics, to signals from gravitational signals, to astrophysics, modeling of the sources, and also more recently to improving the sensitivity of the detector. Okay, so as we know, what was detected is a signal from a binary black hole merger. So this merger has 3 stages. So first you have 2 black holes rotating around each other. When they rotate, this system emits gravitational waves. So the orbit shrinks and orbital frequency increases, and the gravitational frequency is twice the orbital frequency. So you have a signal with increasing frequency and amplitude until the black holes coalesce. Then you have a short impulse, and then they coalesce into a black hole that also vibrates. So you have also normal modes. So at the moment, this signal has been very, very accurately calculated by numerical relativists. Simply, at the moment, you are able to solve Einstein's equations for a binary system on computer very accurately. And this solution matched very well the signal that was actually measured by the detectors. So also we have a very accurate analytical or semi-analytical models which are needed for the extracting the signals from the noise. Because what happens is that we have this signal which is buried in the noise in the detector, and the basic method for detecting these signals is correlating the data with the predicted waveforms. And so what you get at the output is when there is a signal in the noise, you get a large peak, which size depends on how strong is the signal. Of course, we don't know. This signal depends on the masses of the black holes. Also depends on the spins. Which you don't know. So you need to do many such correlations to find, the best one, which gives the maximum correlation, the highest signal-to-noise ratio. So this technique was used. There were others, but this is the main technique that was used to analyze the LIGO data. And in the first observing run of the LIGO detectors, which started in September 2015 and ended in January 2016, basically two gravitational wave signals were detected, and there was a third one which was not sufficiently significant, but matched very well the template. So here what you see is this detection statistic, which is this correlation that you get through match filtering, and this is the number of events. And these signals, their values of the detection statistics, essentially the signal-to-noise ratio, against the background noise. This statistic, when there is no signal and the noise is Gaussian, has very simple distributions, an exponential distribution, but it is not assumed. One estimates from the data this background signal, and then from this one assess the significance. So this was the first signal detected, which was the strongest because it was the strongest. Well, this depends on the mass. It had high mass, and also it was fairly close. And there was another one detected, which was further away, and which had lower masses. Okay. Next, also, so this was the first run. Also, in end of November, the advanced LIGO detector started the next scientific run, and so far in this run, yet another signal, gravitational signals, was detected, and this was a signal again from a binary black hole. And here I show some details. It turns out that these signals from binary black holes are quite strong, so they can also be seen not only through these match filtering techniques, which is the most optimal way of extracting signals from the noise, but also by a time frequency analysis. Here, these are the wavelets transforms. So you see this is the frequency, this is time, so you see this characteristic increase in frequency. Here are the signals from the two detectors against the data, the best fits. The best fit is here. The two signals, of course, the signals, they arrived to detectors at different times, so there was a shift. Also, there is question of orientation of the detectors. So this was taken into account, and you will see that that the same signals arrived to both detectors, and when you subtract them from the data, what you see is basically noise. So now we have essentially we have three certain signals and one very probable. So here are these chirps. Where the chirp ends depends on the mass, as I have been shown. So as I have shown. So this one, the first one detected, has the highest mass. So when it lasts the shortest time in the bandwidth of the detector. Here we start from 30 Hertz, the frequency increasing with time, and this one ends first. So this one has the highest mass. The last signal that was detected had a slightly lower mass, and moreover it was further away. So that's why this amplitude is smaller, because amplitude is inversely proportional to the distance. So now here on this picture we see what are the masses of the black holes that were detected through gravitational waves by LIGO detectors, and they are compared against the masses of the black holes that you get also from X-ray measurements. You see that these masses tend to be higher, though there is also this one which is quite small. It's in line with this X-ray measurements. Here this plot shows the localization on the sky of these signals. One sees that we had 2 detectors, so the localization was not very good. It was just a few hundred square degrees. Another important quantity is the spins of these black holes, and here what is shown is certain parameter, effective spin parameter, which is a linear combination of the projections of the spins of the black holes on the orbital angular momentum, and what is shown here are the posterior probability distributions. One estimates the parameters in this analysis through Bayesian analysis, and the results are simply posterior distribution of the parameters. So you see that these effective spins tend to be around 0. If this parameter is negative, this means that there's misalignment with the spin and orbital angular momentum. If it is positive, it means there's an alignment, and this is important for the astrophysical origin of these sources. So next thing is of course the natural question arises: what was the astrophysical origin of these sources, and how did systems arise? And there are essentially 2 competing scenarios. One is that just was evolution of a binary system with sufficiently masses in the field of the galaxy, where you have that these masses, this orbit shrinks, thanks to gravitational radiation reaction. Then there is some tidal transfer, then supernova explosion. One black hole is created, then there's another one, there's this common envelope phase. So this is one scenario. The other one is that dynamical capture. So it means that these signals, this binary system arose in the globular clusters where many such binary systems are formed. They were interacting, and you had many black hole systems, binary system interacting also with single black holes. Eventually, a binary system was ejected from the globular cluster, and then evolved through gravitational radiation reaction and coalesced. Okay, it's not known so far from the observations. We cannot decide which scenario is working. Maybe both. The other thing is the localization. Here the key problem, when you have 2 detectors, then from the time delay of arrival of signal at both detectors, you can essentially determine the position where the source is on this ring on the sky. You need a 3rd detector, then you can determine the position more exactly. So hence there is a need for the 3rd detector. And there is a 3rd detector, which is Virgo, which I mentioned. Unfortunately, there were certain delays in operation in making this detector work. Nevertheless, thanks to the great effort of the experimentalists, the Virgo detector joined, 1st of August, joined this observational run 2 of LIGO, and we had 3 detectors working for 1 month. And what is more important, we obtained very, very promising gravitational wave candidates that are now being analyzed. So perhaps next month, we should hear more about the results, which should be very exciting. Next thing is some other things that you can do with this observation of gravitational waves. So these are, of course, the tests of general relativity. So here, what is here is the phase of the gravitational wave signal, which is now known, also was calculated not only numerical but also analytical at a high orders during so-called post-Newtonian approximation. And one can test from the analysis the deviations of these coefficients from general relativity. So the first coefficient, which is called Newton, which comes from quadruple approximation, was already tested by binary pulsar measurements, and it's much better than the ones that we get from gravitational wave detectors. But other higher order coefficients can be tested much better with gravitational wave signals from these ground-based observations, because you enter this strong field regime. Then there is another thing, is the mass of the graviton. Some theories predict that the graviton has some mass. This means that we have a dispersion, which means that velocity of gravitational wave would depend on energy, it is on frequency. And when the graviton is massive, this would affect this phase of the signal, so that our templates will be getting out of phase from the just GR model with massless graviton. And so this can be tested, and one imposes interesting bounds on the masses of the graviton, and these bounds improve with more measurements. So with this last detection that we had from LIGO, it's getting even better. Next thing, what is very, very important, is the collaboration with other astronomical observatories. This is because, when you have a gravitational signal, say a supernova explosion, you also have emission of neutrinos. Also, when you have a coalescence of black holes, you don't expect electromagnetic signal, but if there is a neutron star involved, it is expected to be a source of short gamma ray bursts and also other optical phenomena. So a very large program was initiated where the data from gravitational wave detectors are analyzed online, and if there are promising triggers, and this analysis is done in a time less than 1 minute, and there is a promising trigger, they are sent to electromagnetic partners which signed a memorandum of understanding with LIGO and Virgo. So this program worked quite well. Well in the sense that many groups responded and did observations, devoted the telescope time, even for these black hole coalescences where you normally do not expect electromagnetic signals, of course, unless there is really something new, some new physics going on. So anyway, these measurements were made. Next thing is, of course, there are other sources, and other sources were searched. In the analysis of this first observational run, the other sources that were searched were the signals, gravitational signals from supernova, from other binary systems, also from rotating neutron stars, pulsars. There only the upper bounds were imposed. In particular, our group participates in these searches, so we have computer codes that do this, that search for certain known pulsars, and here we imposed a quite tight bounds on the energy emitted from a Crab pulsar. Then also we do all-sky searches for unknown pulsars in the whole of galaxy. So far we have upper limits, no detections, at least no detections in the observational run, the first one. Also very important analysis, search for stochastic signals, and these stochastic gravitational signals, they may arise in early universe from inflation, cosmic strings, phase transitions. And here, what is shown here are the results from searches of LIGO and Virgo data. You get certain upper limits on the energy density. And here also is kind of a landscape picture that compares from other observations like pulsar timing. These indirect limits are limits from cosmic microwave background and Big Bang nucleosynthesis. Simply if the background of the gravitational waves were higher than this, then this will be seen in cosmic microwave background, in the temperature or in the abundances of the light elements in the universe. Very promising is this signal, which is stochastic signal, which is superpositions from binary black holes in the universe, because there are more of them than was expected, and this signal may be seen when the LIGO and Virgo detectors reach their design sensitivity. Next thing is the outlook. So here this band shows the sensitivity of the LIGO and Virgo detectors when they evolve over time. A little bit out of date. This is this Living Review journal where these things are updated. Anyway, the LIGO detectors, they're already here. They reach this point, say upper edges of this green band. Virgo detector started to work and it's already here. Here you see some of the estimates. For example, this question of very important is detection of binary neutron stars. And as you see, these are the predictions. As you see, these predictions are uncertain. So finally, also I will give that these ground-based detectors are not the only detectors of gravitational waves. There is also a planned detector in space, which is called LISA, which will be sensitive to lower frequencies, in particular to binary white dwarfs and also more massive black holes. There is also plans to build a larger ground-based detectors. Gravitational waves are also searched from timing of millisecond pulsars, which can detect background from massive black holes. Also, as we know, from cosmic microwave background, you can, there are attempts to measure the so-called bipolarizations, which now we have. There was this announcement by BICEP2, but it turned out that to not be accurate, and you have only upper bounds from this. Okay, so finally, what the conclusions is, the thing is that general relativity has been tested. So far, there's no deviations from general relativity, and of course, we have new field, gravitational wave astronomy. So I just want to end with a movie, of black hole coalescence. I don't know whether it can be played. Maybe not. I don't know if there is a player that can play this movie. So anyway, thank you very much. Maybe one can play this short movie, just a few seconds, if there is some player here.
Okay, in the meantime, let's thank Professor Królak.
Okay, thank you very much. Thank you. Ten przedostatni.
Sorry, we haven't got time for discussion. Professor Buis didn't give us time for this. So let's thank all speakers of this session.
Never mind. Okay, you can see there, as Professor Taft mentioned, there are many movies on the internet of this binary black hole coalescence made by numerical relativists. Okay, thank you.
Professor.